Okay. Good morning, everyone. Before we start with the next lecture, Casey has a short announcement to make.
Yeah, so after the first lecture, during the break time, we like to try group photo. Are we going to stay in this room for the group photo? Or do we need to go somewhere else? Oh, here. Okay, so we will do the group photo in the front side of the room. Okay, yeah.
So yeah, happy to give the word to Sergey, who's giving the third lecture of his series. And we have a quantum day today, so go ahead.
Thank you very much, Ramon. So good morning, welcome back. This is our third lecture, but as you know, in the format that we're doing this, we're alternating lecture and hands-on. So the next hour will be lecture, as we did before, and then the following one is going to be a hands-on, where you get to do some more fun stuff with quantum circuits and quantum machine learning. So let's recap a little bit. What did we talk about last time? Just briefly, just to set the stage. One of the key things is how do you encode your data into a quantum state? Okay, and there is several ways to do it. The most popular ones are amplitude encoding, and where you encode the vector, the classical vector, as an amplitude of your quantum state or your wave function. And the other way you can do it is through angle encoding, where the angle of the rotation gate is completely determined by the classical feature vector. So different xi's, right, contribute differently to, through a different angle, you can encode this thing nicely onto the qubits. Those are quite popular, and we'll show you some examples of both, and you'll see, get an idea, get a flavor for each one. We also talked about parameterized circuits, which are at the heart of quantum machine learning. It's currently one of the most promising ways to go about things. And the idea is that this is a hybrid system, right? So which has some quantum part, and you offload the key parts. You can offload the key parts to the quantum circuit, especially the part where you can leverage the expressiveness of the quantum computer, the expressiveness of the quantum representation, to do something you couldn't efficiently necessarily do in the classical system. And then you can make a measurement, collapse your wave function. You can do it over one or multiple qubits. And then your output itself is either the prediction or if you're doing something like classification, it's a way for you to assess. Then you can assess classically your objective function, how you're doing, and then you can go back and you can update the parameters of this circuit, the quantum circuit. The reason it's parametrized is that there are these free parameters theta, just like you would think classically in classical neural networks, right? Those would be parameter, your weights or whatever else, things that you can tune. And then that's something that you can update. And we train the whole thing using certain tricks that we talked about briefly last time. We're going to go a little bit more in the detail of that today. So that's the basic setup. And that's why it's a hybrid system, and you take the advantage of best parts of both worlds. Okay, things you can do classically, you should try to do classically. Things that you may have a hope to gain something new, either it's an efficiency, computational advantage, or performance advantage that you can do in with the quantum circuits. Of course, the difficult part becomes, just as when you are dealing with classical neural networks, how do you know what's like the best, what's the right circuit for your problem? And there's some sort of ansatz you have to make, okay? And that's something we'll come back to a little bit later in the lecture. Okay, it's very much an open area of research. In fact, multiple things I'll mention today are going to be very much open areas of research. So I may not have all the answers for you, but I want to give you at least a glimpse of where the field currently is. And as you heard in yesterday's talks, this is a very fast-moving field. It's only been around for, in earnest for about 5 years. So things are moving quickly, and there's a lot of new ideas. And many things have not been solved, which is why it's very exciting for you guys right now. Now is a great time to enter this field and make your contribution, move the field forward. All right, so it's a very, very interesting time to be living if you're interested in this topic. So let's talk about the learning algorithm and optimization. If you remember, we abstracted that out. So let's talk about how that works in this context. So optimization itself is an old branch of mathematics, right? Whose goal is to find, given a function, you want to maximize and minimize the function. Essentially, it boils down to that. And you can cast many, many problems in that way, and including machine learning tasks, which of course you want to minimize some sort of error, right? Your misclassification if you're trying to classify. That's the goal. So suppose you have a real valued function, let's call it the objective function or loss function or cost function, and the goal is to minimize it or optimize it. Well, how do we do this? Normally, we use something called gradient descent, which relies on gradients, which most of you know from freshman calculus, is a vector. You take partial derivatives of a function, and then you have to, of course, be aware of the chain rule. And the idea is that gradient descent is an iterative algorithm with various hyperparameters that you can use in order to find this optimal solution, this minimum. And the way you do it is you measure the local gradients. You take the partial derivative of your cost function or loss function with respect to the weights, different parameters you have, and then you update those weights, you update those parameters in the direction of the steepest gradient. Basically, as if you're coming down the mountain, you take the steepest way down. That's the general idea. There are various hyperparameters to this: learning step, learning rate, etc. Something called momentum. And so there's different ideas on how to get here in the fastest and most computationally efficient way, right? Some of it requires making some assumptions and approximations. And so, for example, there are these different optimizers that you may have heard about, okay, that help the situation. So, for example, something like momentum. How many of you heard about momentum outside of physics? Okay, a few. All right. So instead of just a regular, relatively slow updating gradient descent, you can think of this thing as ball rolling down the hill in our going down the hill analogy. All right. So you add some momentum. You push it in order to dampen those oscillations. Right. That's the idea. Now, this idea you could evolve. For instance, atom. Right. The idea is that now you're introducing an exponentially decaying average of the past gradient. So you're using information from right before that to update that. And it's equivalent to this idea of the ball rolling down the hill with friction, right? So you want it to get to where you want it to go, but you don't want to get, sometimes you want to dampen that out as you get closer to where you want to get to. You don't want to be shifting around too much once you get closer to your optimal. So these different ideas. Of course, there's other things like RMS prop, eta delta, eta grad. Won't go in the detail of this. This is just different ways to optimize this specific problem. Now, how does this relate to quantum? Well, it turns out that we will be able to use stochastic gradient descent, and in some sense, also some of the optimizers. All this machinery that was built for optimizing neural networks could be applied also to our classical and quantum part of our network. So let's look at how that happens. So this is just an example of how these different optimizers, what effect it has on how fast you get to the optimal point, and that in the end they sort of all end up in roughly the same place. How quickly, how efficiently, that's kind of what they measure, what they end up looking like for just one of those representative problems. So here there's an important trick. It's called the parameter shift trick. The people realize basically what you do is you add, you shift your parameter in one direction and the other direction and take the difference, and turns out that is going to be your, you can use that to quickly and efficiently find exactly, actually not approximate, exactly the gradient. The reason for this is that the reason why this is really good is because you can use the same identical circuit, okay, to compute both the function and the gradient. That really helps you, okay? And this is why we can use the gradient descent to optimize also the quantum part of our circuit. Essentially, it's just a little shift in the X, right? And then you look at what effect it has. It moves your Y a little bit. You look at the difference of the two, and that is actually going to be the, essentially your gradient. Now, you can see this as in a simple example here of like a sine type function, right? Trigonometric function. What happens? So here you can see, of course, we know that the derivative of the sine is cosine, right? And so here's what happens if you apply, this is the exact solution, right? And then here's what happens if you actually use the parameter shift trick. They're sitting on top of each other. Okay, so it really works for some basic trigonometry. But you may ask a good question, and somebody asked that question, I think, earlier. Is this really true for all circuits, or is it just some special functions that this is true for? And it's a very valid question, because indeed there are some special circuits for which this will not work exactly, except, by the way, this idea was first introduced in this paper, or this is one of the first papers, I should say, on this topic. Now, in fact, there is a stochastic generalization of this idea, okay, that you can read about in this particular paper, Banshee and Crookes, that you can apply this now to any quantum circuit, any quantum gates that we know. So that's the nice part. So there's a stochastic version of this that makes it general. Now that requires sampling, from random sampling from distributions. A little bit more complicated than this very simple looking formula, but it works for all possible gates. All right, so that's the answer to that question. And this is I'm going to spend a second here because I want you to appreciate this very nice situation where we can use the same circuit, our PQC, okay? Once you get in the quantum part, it turns out we can still use gradient descent, and that's what we will use exactly to update our theta. Any questions so far?
Why don't we can use this tree in the classical?
Good question. Well, think of it this way. So right now, taking gradients is a rather optimized thing, right? There's auto differentiation and so on. You don't really gain anything by this, right? In the class. So the main thing is that, the way that it's currently done is fairly efficient. There's no real need for it. And you still get the same answer. And it should work for many types of ansatzes that you have. But you still have, but this stochastic generalization is what you really need for this to work more generally. Okay, so, and that comes with some penalty. There's some computational penalty to this part. Okay, and to the part that generalizes this. So it's an offset of things. So there is, I think it's a very good question. I'll repeat it for folks on Zoom, why you wouldn't use this classically. And the answer is that for the situations you care, it's already, the way we do it now in the, with this SGD and the optimizer is already pretty quick and efficient. So you don't really need it. But in the cases where it becomes really difficult, it turns out there is a computational price to pay, which actually is a little bit offset on the quantum part, right? That's where the quantum part is actually more efficient potentially. Yeah.
How can quantum get an advantage compared to the classical?
Advantage in what? Yeah. The complicated part is that classically, well, quantum advantage is a whole other question, but we're talking about how to take gradients. Okay, this is a very specific problem. And it turns out that just basic, our usual sort of chain rule, partial derivatives thing, the way you do it classically is very inefficient on for a quantum circuit. Remember, your quantum circuit, first of all, cannot be very deep currently because we're focused on near-term quantum computers. And secondly, there'll be a limited number of operations you can do before your state decoheres. You have to do something to your state. So you try to optimize the number of operations that you do. Usually it's some kind of a gate rotation or entanglement. So you want to be able to use that time for those operations rather than offload to something, something like that. And classically, you can compute that very quickly, and then you can make that update. Thank you. That was a very good question. We can talk more about that. Yes. Yeah.
For this trip, if we want to find the setup, then we should calculate it 2 times for the setup process and setup minus s. If we have an n parameter, then we should calculate the n 2n times.
Yeah, so it has, there is some, if you read this paper, for example, it'll tell you the exact computational cost of this, right, which has some n squared log, n log terms and d. So it still turns out to be rather efficient. So as you saw, actually, I think in yesterday's talk, I think Seth alluded to this part. So it's still going to be more efficient than if you were trying to do the full differentiation. And then, of course, if you have to do it by parts, that makes it even more complicated. So this trick saves you a lot. So it's an important one. Thank you. Very good question. Yes, another question. Yes, yeah. Oh, choice of S. Yes, it is true. I mean, think of it that these are just small shifts. Okay, so normally you make a small shift. It's a small shift. So yeah. You can expand it, sure, certainly you could, but then why would you want to do that? Yeah. Yeah. So this one is not exact. Okay. And now here, okay, this is an important question. Why is it exact? What does it really mean, for the quantum computation? So remember that when we make a measurement, going back a little bit more to the idea of quantum circuits and measurements and so on, as we saw in our hands-on the other day, right? You can say, okay, here's my measurement. Let's collapse the wave function and so on. Let's go ahead and do this. But in reality, right, when you need to sample, okay? And so what I'm trying to tell you is that when these are, in a way, when you sample, you basically approximate the exact, right? Remember when you do it, when we actually showed ourselves that those probability amplitudes and so on ended up what we expected to be, but in order to convince ourselves, we had to actually do it many times, right? That's the nature of quantum mechanics. And so this is the same thing where in a real quantum computer, making that measurement n times then ends up approximating this exact thing. So this is the main little fine point. Even though it's exact, in the real quantum computer and when we want to take things out, you actually need to sample, and therefore that will be an approximation to that exact thing. Yeah, thank you. Very nice questions. Very nice questions. But let's continue. I still have quite a bit to tell you guys about, but thank you. These are very good questions. If you have questions, ask. You can also ask me in the end as well. Now, let's talk about kernels. So you heard in yesterday's colloquium, this is an important area of study in both classical and turns out also in the quantum machine learning. So let's talk about why that is. This also has a little bit of a historical perspective of how the quantum machine learning field evolved. And the idea here, the idea in the kernel is that your input data may not be easily separable in the feature space that you start, but maybe if you apply some kind of a transformation, apply a feature transformation to your input vector, feature vector, you may end up in a higher dimensional space where you may have an easier way of separating your data. Okay, so you trade your original input space for this feature space, and there is some price to pay, but at the same time there is an advantage. This is a convex problem. It's well behaved. You can use gradient descent and so on. What's the disadvantage of this? The disadvantage is the high dimensional transformation, that you're doing. This is a nonlinear thing, by the way. It's one way to introduce nonlinearity. And the point is that it may not capture, you wanted to capture some of these nonlinear interactions. You may not be able to do this, and it's not, it's a little bit slow. That's the real disadvantage here. So, oops, sorry, I keep pressing the wrong thing. So if we're going back, that's what's happening, okay? So let's go forward. So there is a trick here. there's a classical trick in machine learning called the kernel trick. Why is that? Why do we, first of all, need this trick? We need this trick so that our functions are efficient in this high dimensional space, right? Because it's a very large space. The trick, there's a big computational bottleneck there. So how do we avoid this? We avoid this by computing the inner products. It turns out all you really need are the inner products, okay, of, instead of the data points themselves. Okay, it's the contraction that you need rather than the data points, which makes this much more efficient. So for gradient descent, what that means is you need only the inner products of your vector pairs, right, to learn this classifier that you're trying to get, this separation, this hyperplane. It's a trick. You don't have to compute everything for your points in this high dimensional space. Instead, you do the inner products. Why is this interesting? Quantum mechanics, inner products, our quantum computers are actually going to be ideal for computing inner products, right, in this sense. So it's a very interesting thing that we may be able to use this kernel trick, not just in the classical sense, but in the quantum sense. Now, the question is always, well, what's my kernel function? Because you have to assume also some kind of an ansatz here. And usually, you can try different kernels. You can try a linear kernel. That's usually not the most interesting idea for two vectors A and B, okay, A transpose B. More often in classical machine learning, you make some other kernel ansatz. Maybe it's a polynomial kernel, maybe it's an RBF function, radial basis function, essentially a Gaussian difference. And there are other things like exponential, Laplacian, sigmoid. There's different kernels, and this is where this becomes quite interesting because these guys are rather general, okay, but they're not guaranteed to be the best. And you actually don't have such a guarantee. So if you ask me, what is the best kernel? Okay, I can't give you an answer, right? It may be problem specific. This is part where your knowledge of the problem and an ansatz you make makes a difference. Your understanding of where does your data live in this high dimension, where, actually, plays a role. So this is great. This trick is wonderful, but it doesn't really tell you, everything. There's no free lunch, okay? And that, of course, extends also into the quantum world, okay? You have to make an ansatz, and based on that ansatz, your performance will change. So the idea, again, is that with quantum kernels, it's a very nice way for us. I think there was a question yesterday, how do we capture the nonlinearity, right, of neural networks? In this particular step, where we're going to map a classical feature vector, now we're going to map it into Hilbert space, right? What do we know about Hilbert spaces? Inner product is going to be always defined there. So it's a key part of the Hilbert space. And so it's a natural way to do this thing and produce a quantum feature map. Okay? So what does it really mean? What does the quantum kernel trick really mean here? It really means that when we look at two states, like suppose we prepare our quantum system, right, in one state, and then we prepare it in another state, okay? What we can do is when we take this inner product, this really means overlap between the two systems, the two states, I'm sorry. So this is quite interesting because it tells you what is the overlap between them, and then you can use this later on in some kind of an algorithm. So it turns out that there are algorithms such as support vector machines, which we'll talk about in a moment, that in classical machine learning leverage this kernel trick quite a lot. So we'll be able to build a quantum version of that. And in fact, that was one of the very first quantum machine learning algorithms because it was a very natural extension where you may be able to just say, I'm going to keep my SVM algorithm the same, and all I'm going to do is I'm going to use my quantum computer or my quantum circuit in this particular case is just to compute these kernels. That's all. And it's going to be more efficient and so on, and I can just make that work. It turns out you can do more than that, but this was certainly one of the first natural extensions from classical into quantum. So what does it really mean? Let's look a little bit about support vector machines. And the idea is that, of course, you can use this. I think it was also introduced yesterday. and earlier too, you can use them for classification, linear or nonlinear, regression, whatever else you want to do. And the main idea is that you're going to move yourself into this high-dimensional feature space, utilize the kernel trick, and you're going to have a new feature map. And the idea is that you want to create the why is this possible separation or road between so-called margin, right, between classes. So the idea is that even though it's not separable in your input dimensions, you may be able to do better if you go to this hyperdimension and you use a hyperplane to partition this. You're ultimately trying to find this hyperplane, okay, which is basically some, you can think of it as a line, which is, in higher dimensions, right, hyperplane, where you want to separate the data. So essentially, you're trying here your data points of the different classes. You can compute, there's a margin, and these are called support vectors, which actually correspond to the vectors to those individual points. And the idea is that you want to maximize the margin, which is going to be equivalent to this particular minimizing this particular metric. And what you're really trying to do, okay, in the quantum version of the same thing, okay, is you want to replace the part of this SVM algorithm, okay, with these quantum feature maps and quantum kernels. Okay, so that looks usually something like that. You have some, you have some gates, and now the idea is that now you're going to map your problem, your classical problem, onto the block sphere, okay, in a way that's going to essentially maximize the separation between the two distributions, okay, under this particular ansatz, and you'll utilize quantum kernels to compute these overlaps and so on efficiently. So that's the idea, and this was proposed by Havlicek et al. In 2019, and it's been used certainly with some success since then. Now, certainly this is just one example. There are others, and we're going to now, there's of course a deep connection between support vector machines and neural networks, right, in classical machine learning. So there's quite an interesting connection also in the quantum world and quantum kernels also with quantum neural networks that people are looking into now. Now, let's talk about one other cool thing that we can do. It's something called data reuploading. Now, I like this thing because this is analogous. We heard in the first day, in a very nice lecture on the first day, we heard about this universal approximation theorem for neural networks, right? And there's this kind of an analogous thing in quantum machine learning. And this has to do with something called data reuploading. And today you get a chance to play with this also in the hands-on. And the idea is that if you have a parametrized quantum circuit, let's say a classifier, and here you have, let's say, these are single qubit rotations, for example. The idea is that you reupload your classical data multiple times, okay? And every time you do that, okay, you're basically resetting your state. Okay, it's almost like this idea where the classical data, you're feeding it in chunks. Okay, but you'd fill it multiple times, and this is a really problem that you have before. Once you make some rotations, you lose information. You don't have that current information from where you started once you moved away, right? And this is a way of providing your system that information again. And it's interesting that you can show, and you can read in this paper, that in fact, that's kind of all you need to build a very nice classifier. Of course, there's no free lunch, just as in the universal approximation theorem. Okay, it doesn't tell you, okay, how to find that optimal ansatz. And as you know, in the classical sense, you need to know how many neurons, what's the width. It's not that you just automatically are going to get your answer and it's going to be the most efficient way. It's a similar thing in quantum, but the nice thing is that it's possible. Okay, and this data reuploading is a powerful technique that you can combine with other techniques to possibly improve. But you can actually use it completely on its own. So today, in our second session, one of the things we'll do is we're actually going to build a data reuploading circuit and see how to use it in the context of classification. So I refer you more to this paper and others that followed to learn a bit more details about this data reuploading. Okay, so what I want to do next is I want to talk about quantum neural networks, QNNs. So let's go back to parametrized circuits. Remember, what are we after? We're after an extension of this classical neural network idea. We have these free parameters theta, and we want to introduce some quantum layers. Normally, that means some rotation gates and entanglement. And we're going to train this thing with backpropagation and gradient descent using the parameter shift trick that we learned about today. And actually, it's also going to be in our hands-on activity. We didn't get to that last time. Some of you maybe did, but we'll get a chance to practice this. Now, this requires an ansatz of the circuit, all right? And this is why you have no free lunch. And this is the part where some knowledge helps you. Think of it as like coming up with the right neural network architecture, okay, for your problem. So you need some kind of a circuit ansatz, and there's an infinity of infinities of these. And so you need to be, you can either sample, you can try to figure out what an optimal thing is, but it's not so trivial. And it turns out that many classes of these lead to problems, kind of like vanishing gradients that we talked about. There's something called barren plateau. I won't talk much about it today, but not every circuit is going to lead to a good solution. That's the problem. And so you can't just say, give me a random circuit and go with that. So you need to introduce regularizations and certain other tricks in order to avoid this problem. And so for that reason, you can't just, you will need over time, if you want to optimize your circuit, it's not just optimizing the parameters of the circuit, but if you ask what if I just pick a random circuit and try to optimize that? It's not always going to work. But there are some ideas on how to try to optimize also the architecture, right? The ansatz. But it's a very, very open area of research today. So just be aware, okay, that this was an assumption that you make, as you usually do also sometimes in classical machine learning, right? It's your best guess to what the best model will be for solving a problem. And these can be quite different. So, sorry, keep going back. Now let's go forward again. Quick word about tools. On Tuesday, we used PennyLane, but we should certainly discuss all the other tools on the market. PennyLane is fantastic, of course, but also there are other things like Qiskit. Okay, there's also Cirq, which is made by Google to express different circuits, and then of course there's TensorFlow Quantum, on which you can then use it with. Of course, PennyLane kind of works with all of these, but there's a whole different communities around these open source tools. And to help you run all these things on classical computers in order to simulate them, or eventually also on quantum hardware, NVIDIA put out this very nice thing called QQuantum, right, SDK, where which is optimized, whether it's simulation, in simulation, for instance, how do you run these things on GPUs efficiently, multiple GPUs if you have those. So these can be somewhat expensive computationally, and so these things help in the long run. So make sure you're familiar with all those tools. Okay, let's look at an illustrative example. In fact, it's going to be the example that we have talked about already on Tuesday and Monday, and let's talk a little bit more about that. So the key question we want to answer there, okay, and I'm going to again show you the same picture you saw in Tillman's talk. How do we, in particle physics, how do we fully exploit the information, the richness of information in our detectors in order to do physics? And it turns out one of the most powerful ways is to combine modern machine learning, deep learning algorithms that are able to extract features, are powerful on high dimensional data, and we usually pair them with low level data. That's a very powerful combination. So we don't first extract features and then do some machine learning with it. We actually start at low level data representation. Okay, so oftentimes that means even bypassing some of the current reconstruction steps, because those already make some assumptions, you have some data loss. So going back, it's almost like analogous to computer vision or graph neural networks, where you're operating directly on point clouds and pixels rather than things that have already been pre-clustered for you in some way. Okay, and this is what we call end-to-end deep learning. You can read all about this. There's a number of papers, and in fact, It's used also in different searches and so on. But this is really kind of a very powerful idea. So as a simple example of this idea, right, we can look at the CMS detector. There's information about different particles. There are different detectors that are designed to detect and reconstruct, measure, for example, calorimeters measure the energy deposited by different particles. For example, electromagnetic calorimeter made up of crystals, it measures the energy deposited by electrons and photons. There is a tracker, right? You can see different tracks. It's sort of a pattern recognition problem. Then you have the hadronic calorimeter and muon system out there, and there's magnet and so on. So charged particles bend. Of course, photons are not charged, so they go straight, and they don't leave a track. But they leave stuff in here in the electromagnetic calorimeter. Jets leave stuff more or less everywhere. Muons, right? They go right through. So why am I showing you this? There's a wealth of information here. Okay? If you look at the low level, in order to say I have found the Higgs boson itself, you don't say, how do you do this? You do this statistically. You first look at all the decays. You look at all the final products. In the collision, then you work it backwards. You want to identify all the particles, okay? And that requires often combining information from multiple detectors, okay? So that means you can look at the whole detector representation in order to find these different things. So as a simple example, early on, around 2016 was one of the very first application of convolutional neural networks. In this case, this was for jet images. So the idea was you take a calorimeter, okay, which is cylindrical, you unroll that, and then you can, use each, you can basically treat it as a camera, okay, and then you can, use the, in this particular example, they made some transformations and so on, and then you can apply convolutional neural networks to that data, and that was the very first example of what these look like. Things have evolved quite a lot since then, but maybe we should just spend just a very, I'm not going to, I'm sure you all already know a little bit about convolutional neural networks, but basically, I won't get into too much detail. Now, these were, of course, inspired by how our own visual cortex works, and the idea is that you synthesize things. So basically, you're compressing information. You also, there is some translational invariance, so you try to pull over. Pooling, in this case, means combining information and only pruning it and only letting part of it pass. And you synthesize things over locally to enforce this translational invariance. This is an early model that inspired CNNs. Of course, CNNs look something like this. You have your two-dimensional matrix, right? These different pixels. You have these different convolutional layers, max pooling layers, and so on stacked up, and then maybe some fully connected part, and then you make your predictions. And the key part here is you have these feature maps, which is the result of a convolution operator performed on the previous layer. Okay, where you're essentially moving this, you're multiplying these out to produce these new feature maps. These usually smaller sized feature maps. You're moving it around the image to convolve with its neighbors. Now, in the case of pooling, all you're doing is downsampling. So you take, let's say, maybe the average or the maximum pixel of each one, as you've heard I think in one of the earlier talks. So in the end, this helps you to introduce some kind of invariance to small local translations. Okay, that's what that gives you. Now, an example of this end-to-end learning I showed you, in fact, this is our challenge that we looked at earlier, and that is how do we separate, for example, electromagnetic showers in the electromagnetic calorimeter without any other information by looking at the energy depositions of electrons and photons. It's interesting that if you average these out and you look at it by eye, if you really, really squint, you might see that the electron one is slightly asymmetric. This is because it's simulated, and these are positrons. So because of magnetic field, there's a slight asymmetry that is hard to notice if you don't really squint, but if you really do, you might notice it. But it turns out that convolutional neural networks are really good at solving this problem, and hopefully many of you working on the classical particle images challenge have found that. In fact, you can extend this idea to other particles, like, for example, quarks and gluons. And by the way, if you've never seen quarks and gluons, here is a detector representation of quarks and gluons averaged over many. So these are not the exact quarks and gluons. These are jets, of course, produced by these quarks and gluons, but this is what they look like, okay, in the CMS detector and different detectors. So you can again train these sort of algorithms, deep learning algorithms, to identify it. So here's how things have evolved for jets. You can see the 2015 version of a jet, very pixelated, very core. Now this is what they look like, you know, a little bit later. There's a richness of information coming from all these different detectors and tracks and so on. You see how much richer it is and how much more amenable that's going to be for even for CNNs. But you don't have to do, of course, CNNs. This is just one of the representations. So here's again this jet image for, you know, quarks and gluons. You can see, what that visually looks like, at least in the average space. And you can, of course, apply it to other things like boosted tops and things like that. So you can read this in all these different papers. And clearly, for images, CNNs and other type of computer vision algorithms work well. Of course, also newer algorithms like vision transformers and so on, they also are applicable to this representation. You can also turn these things into point clouds and graphs, in which case you would use things like graph neural networks and so on, which would map nicely to that problem. But that's the kind of problem that I want you to think about. And now let's talk about quantum part of this. So a quantum CNN is basically going to be an analog to our classical CNN, where now we're going to add some quantum layers, right? So what does classical CNN have? We have convolution and pooling. So let's actually offload that idea to the quantum part. So the idea is that now we can do quantum convolution and quantum pooling, which requires separate circuits and connected circuits for each part. The idea is that you apply these parametrized gates, meaning that you can train them, right? And to, in this case, adjacent qubits. It's sort of the idea of doing this convolution over adjacent pixels, right? This is a similar idea. You can apply pooling where only part of the information goes through, okay? And that's the main idea here. Again, and this was first proposed in 2019, not very long ago, by Kong Choi and Lu King in 2019. And you can still train this thing in a very similar way as before, using all the tricks we've learned about. So visually, this looks like this. Here's your cat or whatever, your electron and whatnot. And you have these different layers, all right, in your PQC. And notice, okay, now there is going to be this convolution part in between the qubits, okay? And notice even further, there's a pooling layer, okay? And now you're contracting it. So in the end, you end up with only one out of your 2 qubits, right, going forward, or whatever other, there's different variants of this, but that's the basic idea on the quantum side. And then the rest of it works as usual. You bring it back, you optimize, you do gradient descent, all these tricks as before, okay? But you perform this part on in your quantum circuit, right? That's the basic idea. So here's an example. By the way, this uses the same electron photon data set that we're all should be familiar with by now. So of course, because you need to make it realistic, you cannot use 1,000 qubits, right? So this is just for a very small number of qubits, and for this you need to downsample a little bit the representation, and you can actually see, okay, that here's some hybrid. These are also hybrid type. You can see what happens when you add these quantum layer. You can look without the quantum layer, the loss, and then of course, and the accuracy. And you can see what happens when you add different types of quantum layers based on different types of rotations and entanglements. So this is just a very kind of basic example in this very basic case. And you'll get a chance, of course, to play with this in our, Casey, yeah.
So were you able to see any advantage, at least with this example?
Yeah, no. At the moment, it's parity for really simple cases because you're limited by number of qubits. But remember, if you're limiting the number of qubits, that limits the number of operations that you have. So to make it fair, you have to also limit the classical, right? So that really hampers the classical. So as you can see on this simple example that I was showing you, right, the best kind of CNN will get 0.8 ROC. For instance. But if you say, I can only use 100 operations, so it's not my million parameter ResNet or whatever, 100 million parameter or billion parameter vision transformer, right? Or what my fancy transformer, right? That you can't compare the two. So when you make the fair comparison, they are, there is about parity And people claim there is some advantage for low statistics, but I'll talk a little bit about that later. But anyway, at the moment, it's at the state of parity. But the interesting thing is what happens when you go to more complicated problems, like let's say the quark-gluon problem, okay, or maybe this boosted top one. And the more, it turns out, the more complicated the problem, the more, it's also true for classical ML versus non-ML. Okay, it turns out that the more complicated the problem, the delta of advantage, there is certainly more to gain, okay, than there is for a very simple one. So this is a rather simple one. So you don't really expect to have any advantage, and you don't see it. But you have parity, which is already important. So let's continue on. I want to tell you a little bit more also about a few other things. I know there's not a lot of time, so I'm going to speed up a little bit. So quantum GANs, we've heard about them very briefly in Professor Lloyd's talk. So the idea is that now you have two neural networks, two agents that are competing against each other. Let's say maybe it's a counterfeiter that tries to make counterfeit images or checks, and then there is another network, right? This is the generator, and then there is the competitor, the discriminator, who needs to figure out if this thing is real or fake. And so while you train them together, it's a minimax game. Both get really good at each task. So the generator gets really good at making fakes, right? Realistic fakes. And the discriminator gets really good at figuring out if it's a fake or not. And so the classical GAN, has been around for almost a decade. It's the ideas of Ian Goodfellow and others, as you've heard about in Ramon's talks. Of course, the idea is that you want to produce an image out of random noise in the generator, and discriminator guesses if it's fake or real, ultimately gives you a probability. And the idea is that you do gradient ascent for the discriminator, gradient descent for the generator. There are different variants of this, but ultimately it's a game theoretical problem, a minimax, so-called minimax game, and Nash equilibrium. And one of the things that can plague you, which have more or less been solved in a classical sense, but not yet in the quantum, called mode collapse. And mode collapse is what happens when your network learns to, basically what it does, it outputs very few representations. So you end up like kind of for a variety of your inputs, you end up showing kind of a very limited variety of outputs. Okay, it sort of like collapses to certain mode. Okay, and it can be overcome in classically through regularization and some other tricks, different types of GANs. But this turns out to be a serious problem also for the quantum version that I'm going to introduce in a little bit, which prompted my question to Professor Lloyd. And this is a very active area of research, actually. So there's some early, I'm going to show some basic convolutional GAN from 2015. You can also, obviously put convolutional, I keep saying gates, but in this case, layers and so on. But ultimately, these are gates. And then the idea is that you can also build a quantum version of this. Okay, and the essence of that is you replace the generator part or the discriminator part or both with PQCs. Okay, and this requires some kind of an encoding circuit, of course. And then here is, for example, like a PQC on 4 qubits. This happens to be one of the GANs, and this was actually built by our team some years ago, actually, as part of this Machine Learning for Psi Google Summer of Code project. So this was Alcade Cheng and Ru Zhang and myself. And the idea here is that the output is the expectation value of your measurement at the end. And then you can go ahead and train these things. And I can show you just very basically what happens. And you can see that it starts from random noise, and then it starts to look like those in this electron photon example, right? You start to see something that resembles what you should get, but in fact, it's mode collapse, okay? And so you can't say, oh yeah, this is great. There's a quantum advantage to our quantum GAN. In reality, you still have to overcome this problem. And this, in fact, turns out to be the case for many of the current quantum GANs. Okay, so in the interest of time, I put a few links so you can read about the different quantum GANs that have been proposed. Many of them suffer from this problem. So, but that's the basic idea. I want to talk also about some other architectures in maybe the remaining few minutes. So let's talk a little bit about quantum graphs, quantum transformers, which is also some of the newer architectures, both in machine learning, but also certainly in quantum machine learning. And graphs, definition of a graph, you can pretty much, it's a network of edges and nodes, relationships between the nodes, for example, and you can express many things on a network as a graph. And the idea is that you can connect them in different ways. You can look at k nearest neighbors and so on. You can define something called an adjacency matrix, which is the weight of the edge between two nodes. And this is a trainable thing, so you can train it, right, when you're training your neural network. So the idea is that the state of your node depends on your neighbors. Why is this good? Because you can express any neural network on a graph. Much of the data you can actually turn into a graph. It turns out that even a matrix, like a simple two-dimensional grid, you can think of it as a very simplified, collapsed projection of a graph. It's also a graph. It's a special instance of a graph. But in reality, if you're dealing with point clouds, high-dimensional point clouds, graphs are going to be natural representations there. And it's a very good approach if your data is not living in this regularized Euclidean space. And the other nice thing is that graphs allow you to propagate information across the graph. Okay, and there are different types of graph, whether it's message passing and different types of learning that you can do that help you pass information long-term. Okay, long-term dependencies. In fact, that's also a powerful idea for a new thing, for a new approach called transformers, which we'll talk about in a moment, where also long-distance, long-range dependencies turned out to be useful if it's something useful for the problem. So the idea is that you can use these things to predict link predictions. For example, in social networks, when somebody says, hey, this might be your friend, by looking at the networks and the overlay and so on, you can actually use this to say, oh, there should be really a link here with this sort of strength. And then if it's above a certain threshold, they'll suggest that friend to you. Is one idea. Of course, there are many others like protein folding, AlphaFold, and so on. There are many problems that have been solved efficiently with classical neural networks. You can extend this thing. Actually, in particle physics, I'll just briefly flash this classical idea for a generative model. Okay, and Ramon has talked about different generative models, scans, and normalizing flows in variational autoencoders. This thing is a combination. This is a work of one of my former graduate students and undergraduate students, where we basically combined graphs as representation of the data. So you drop all, in the case of images, you drop all these empty pixels, you build graphs over it, and then it's a combination with a variational autoencoder. So the idea is that you learn on the graph, there is some pooling operations and so on, and then you can actually use the sampling part of the VAE, okay, to give you this generative model part. And it works really, really well for this sort of end-to-end representation of particle physics events. So anyway, the question is, how do you make a quantum version of this? So how do you make a quantum graph neural network? The idea is that you basically, the same as before, you replace some parts of it with a quantum version. So for example, in this case, you use parametrized Hamiltonians, usually applied multiple times, and the interactions of these, the topology of the interaction is what you want it to be for your graph construction. So you want to map that onto the kind of graph that you want, and there are different ansatz, ansatzes in plural, that you can come up with. You can have a convolutional graph, convolutional type of network analogous to the classical graph convolutional neural network, where the parameters are now connected spatially with these convolutions, as we saw in parameterized circuits and CNNs. Similar idea. You can have a recurrent version, which of course now works over multiple qubits. And so the idea is that this was proposed around 2019. There's new ideas also that have come out since then, but seems to be a promising idea if you're working with graph representations. Currently, small graph representations, right? Given the near-term qubit possibilities, but certainly a promising idea. This is also at the front of research today. As we know, transformers are also the hottest things around, right? So ChatGPT and language models and all, many of you have heard this, but of course what's driving that are transformers. There's this classic paper, Attention is All You Need, that kind of got things started. And the idea is that you don't need any recurrent convolutional layers, just attention plus some other stuff, some basic stuff to actually capture the same ideas in sequences. And this was a significant improvement for natural language processing over other types of things like RNNs LSTMs, and so on. And the idea is that, now you have this attention part, right? And you have these different embeddings, and there's different encodings. Now, let's put on our quantum hat, all right? What do we see in the classical transformer that could be not easily, but naturally replaced with a quantum circuit? Anyone have ideas? First part, encoding, all right? You have to encode. How do you efficiently encode? That is a big thing that there's a very good way for us to do this. What else? What about attention? Do you think we might be able to do attention, quantum? Well, the way forward has been proposed. Now, first of all, on the classical sides, first let's spend a minute there. You all know about GPT, which GPT 1, 2, 3, 4, OpenAI. The idea is that you have some pre-training, and these are very large models, of course, and not the best thing for the quantum. So there's, of course, you need something smaller. There's also another approach, right, where you have an encoder, which is just a bidirectional encoder part with transformers. There are different types. There's just encoder types. There's bidirectional. There is this pre-training. There are different ideas on the market. But in any case, there's also vision transformers, which work really well with images. Okay, they're very competitive. In fact, they've been shown to outperform CNNs for many classical problems. And this is a classical VIT, so-called vision transformer. It's quite a large model. But here you notice there is also this multi-head attention, and then there's this fully connected part. It also works as an encoder. And there is also this embedding. And you split your images into patches and so on. You pass it through this, and then the attention tells you what you should pay attention. So it's basically a weighted matrix, right? This is a weight that you apply to these different parts of it as it goes forward. So it tells you, you can actually train that, and that what powers these different types of transformers. So you can use it with images, you can use it with text, you can use it with any sort of representation. So the quantum version of this is you replace this part, several parts with a PQC, in particular these fully connected layers that you need in the encoding, but also the attention mechanism. And there's multiple papers. So here you can see there are different, in the classical sense, there is there's this matrix, right, of these attention weights that you learn, right? So in the classical sense, you're learning W and V, and so you can represent this problem also with a quantum circuit, which requires you to do some data loading and some other stuff. You can read more details in this particular paper by Shirat et al. Recent paper on a quantum vision transformer. There's other types of ideas also for natural language processing, and also a combination between graphs and transformers. So there's a quantum graph transformer, which has been proposed recently, which combines some of these ideas together. Okay, and the idea is that you may even be able to combine some of these things into one circuit. You can do them individually. You can do attention on its own. You can do the other part on its own, and so on. But there's ideas that you may be able to combine it, and maybe this is where some of the advantage can come in the long term. As you can see, this is a very, very happening, very open area of research. And so I don't have time for this. I'm gonna talk a little bit about it in the beginning of the next one. But there is some more stuff, some more interesting stuff. So I think we're out of time. So I'm gonna stop here and answer any questions you might have. And then we'll come back, and I want to tell you about one more cool thing about how knowledge of physics helps us in deep learning and possibly in quantum deep learning, very briefly, and then we'll get into the hands-on. Thank you very much for your attention.
Thanks a lot. Are there any quick questions?
I have a question. So you introduced the various library like Penny and Tensor Quantum and so on. So as a starter, we need to choose one out of these, right? Then is there any suggestion and the reason for the suggestion? Can you ask?
Yeah, good question. Well, I am biased, so I'll just give you my biased opinion. There'll be others, they'll tell you different. Personally, I think Penny Lane is the way to go. Why? Because you can use it on its own, as you've seen in our hands-on activity. You can just program the whole thing there. You don't need anything else. It also has plugins for everything else. So if you want something from TensorFlow Quantum and Circ, you can use the plugin to do it. It also has a nice integration with QQuantum. Okay, so you'll be able to also do things with GPUs and multiple GPUs. Now, there are some nice features also in each of these, but nowadays, when somebody comes up with a new idea, another framework tries to make sure it's there. So Penny Lane is my recommendation, but we've also used TensorFlow Quantum with some success. Personally, I'm not as familiar with Qiskit. I don't really use it too much, so maybe it has some very nice things. I just don't use it a lot. But it's also built by IBM, so if you're working with IBM hardware, maybe you want to also take a look at Qiskit. But also all these other things. This is a community that certainly is in a similar situation where machine learning, deep learning frameworks were, let's say, 5-6 years ago. There was multiple frameworks, and most of them, some of them didn't survive, but some of them, main ones did, especially the open source ones. So PyTorch and KIAS and so on. And so this is kind of like the situation now. So I would suggest Penny Lane, but that's my own personal preference. Yeah. Yes.
So which part of the QCNN is activation function in QCNN?
Yeah, so remember that activation functions, right? So in a classical neural network, right, you are, that's basically the ansatz you make for the transfer function, right, for your neuron, and whatever it may be, ReLU and so on and so on. And you try to basically say, okay, well, I need to capture my nonlinearity and things like that, and then you may need to do it. And as you heard also yesterday, one way that you capture this part in the quantum part of it is actually through the embedding. Okay, so that part takes care of your nonlinearity. So you have some gates, okay, itself when you try to set up your state and so on that take care of this part. So in fact, all the PQC operations, they're unitary, right? They're linear. And what makes it interesting, there's something else we didn't talk about. Maybe I'll talk a little bit in the beginning of the next section. Maybe let's come back to that also in the beginning of the next section, because I also want to stress this idea that the part of the PQC, okay, is really good also to learn symmetric functions, which is what you want to do in many settings. So in principle, you can, this is not the part that you need to come up with that's different. It's not. It's not something that you necessarily need to do differently. Although some people have ideas on how to implement the neurons directly onto hardware. There are very interesting ideas, and I certainly didn't talk about that today. We focus on parametrized circuits in quantum machine learning. There are some ideas, and there is some promise to those ideas. It'll take some time. The idea is actually when you're building the quantum computer itself, you can actually try to build the neurons into the hardware. Okay, so you can actually build a neural network using some quantum system directly, in which case you may be able to put the ansatz of your activation function straight onto your system, whether it's through neuromorphic approach or through some ion, spintronics or whatever. There's different ideas for how to do it in real life. But that is certainly one way that you can actually couple the two things on the actual hardware. Yeah, here we're kind of abstracting that part out, so you don't have to. This does not become the critical part to your circuit. Thank you for that question. I will come back to the symmetry part. There's more I want to say about this, but I think I'll come back to it after the break. Yeah.
Okay, it seems there are no more questions right now, so let's thank Sergey again, and we go into the break. And then remember that we take a group photo now.
Oh, right, yes. Thank you, everyone. Yeah. We'll see you in a little bit. Yeah.
Stage is yours.
All right, so welcome back, everyone. Now, before we get to the hands-on, I want to talk about one more topic very quickly, very briefly, just because I think it's maybe interesting for many of you in the audience. It's a very active, very open area of research, so not all the answers are there, but, well, the answers are there. Maybe they're not all known to us yet. So anyway, I want to talk a little bit about physics and quantum deep learning. Now, this discussion starts, I'm going to focus on one particular topic in physics, something called covariance, right? And if you look at this quote by Albert Einstein about the general laws of nature, in essence, he said that they should be invariant with respect to any sort of substitutions, okay, for all systems of coordinates. This idea that, you know, there is some covariance here. So physical quantity should transform covariantly between different frames of reference. That's the key idea, okay, which we know is very important to theoretical physics or understanding of the world. Now, this idea, in fact, I want to give you an example of something like, now it deals with symmetry groups. So let's look at a very simple example of gravitational lenses, okay? Now you can actually take some image of an object like an Einstein ring, since we're talking about Einstein, right? And you can see that you can apply an identity transformation, you can rotate it by pi, reflect it, or whatever else. There are different symmetry groups. This happens to be one of such symmetry groups, D2, right? And so the question you can ask is, you know, in deep learning, you can actually use this concept of covariance or gauge invariance, which, you know, we're all familiar with from relativity and quantum field theory, to design networks that are naturally going to obey a certain symmetry. Why is this important? It's important if you know that your data comes from a distribution that has a certain symmetry. Then it turns out you can say, I'm going to ignore that information and try to learn it. It turns out to be a harder task than if you know the symmetry and you design your network in such a way that it's going to be invariant under that symmetry. So you don't have to discover it. So in machine learning, oftentimes, if you don't want to assume your symmetry, you'll do all kinds of data augmentations. Okay, you'll rotate the cat, you'll resize the cat, you'll do whatever things to show your model the cat from all the different angles, so it's not just recognizes the cat from the front, right? If you only show it the cat from the front and then you show it from the back, it's not going to know it's a cat, and so on. So it's important to capture that symmetry. You need to either embed it in the data, show it to your model that's able to learn it, or you can be smart and you can pick a model which is going to respect, let's say, a rotational symmetry or some invariance. As we all know, convolutional neural networks already have some invariance to local translations, right? Because of pooling and convolution. So the point is that they already introduce some kind of invariance, but this idea of covariant equivariant networks is actually a very active area in machine learning. Okay, there's some papers, some key papers by Risi Condor and others that show you how to do this, back swelling. And the idea is that for the case I showed you, there is a dihedral symmetry that I want to use as an example, but in fact can be any isosymmetry. If you know your symmetry group, then you can actually embed that into the network design, either in the design of special layers that respect that symmetry. Maybe the symmetry is Lorentz invariant, so you can build a Lorentz invariant layer. If you like, there are Lorentz invariant layers and Lorentz invariant neural networks. If you have some other symmetry that you want to embed, let's say it's some group like this, you can actually embed that also on the level of convolutions. You can embed it on the level of feature maps. You can embed it even in a loss function. There are many places that you can do. You can penalize, you know, your loss function, you know, due to some symmetry. So that is a key idea that actually is important in the deep learning model. So I want to show you an example, and this example also comes for the same Einstein ring I was talking about, what happens if you rotate normal CNN, right? You train this thing, you rotate the input, all your feature fields move, okay? Problem. But if you then try an equivariant neural network in particular, basically one of the key steps in it's going to stabilize these feature fields, and then you're going to get an invariant representation to a particular symmetry group, in this case, you know, rotations and reflections and whatnot, and then you'll find that the performance of such a network, equivariant network, is often surpasses the performance of the one that does not use that symmetry. If they are the same, oftentimes you get to the solution much quicker. So it's definitely the way to go if you know your symmetry. We don't always know the symmetry, but if you know the symmetry, you can go ahead and use this idea. Now I want to make an extension of this idea, just so everybody here can think a little bit about this, into the quantum world, into the quantum machine learning world. The idea here is that most of your layers, there's rotation gates and entanglements and so on, these are unitary, right? Remember that in our PQC, we're doing unitary gates, and these are actually quite good at learning symmetry. So the gates that we've talked about can learn symmetric functions. They're actually quite good at this. So you can think of building quantum equivariant models, and I put a few references for some ideas, some recent ideas on how to do this, to actually, maybe there might be some possible advantage there over what we can do classically. So it turns out that the setup of the problem might be also quite good for equivariant models. Now, we don't have time to go into this more, but I'll point you to these papers, and this is a very, very active open area of research. And perhaps one thing I will show you before we continue to our hands-on activity is, let me go back over here. I want to also advertise, and I see Tom's online, so great. I actually want to show you on the Machine Learning for Science organization that I mentioned. If you look at the Google Summer of Code this summer, and there's many different projects and NASA and so on, but if you look at quantum projects going on, I know it's a little bit hard to read, but you have quantum GANs, quantum graphs, right? Contrastive learning, equivariant quantum networks, quantum transformers. All these ideas we talked about in the first lecture, there is projects and in this direction. In particular, Tom also works on one of those projects, the Quantum GAN project. So with that said, I'm going to stop here, and I'm going to switch over to our GitHub, and we can go back to what we were doing. Now, first of all, before we start, let's just remind ourselves what we did last time. Last time we looked at the basics, right? We looked at building circuits and so on. And I don't know if everybody actually completed all of it, but if you want to see some of the things we discussed today, maybe Tom can just quickly, when I turn over to Tom, maybe he'll run us over a little bit also the second half of this, because it has to do with optimization, okay? Something we discussed earlier. So that will be our first order of business today. And then the other things I want to just quickly point you to, what we suggest you to do today, we have a notebook for quantum deep neural networks, basic quantum networks, okay? And we're going to look at a very, very simple circuit using this, the problem we gave you guys. We already looked at the classical one. Number 5, this is the data re-uploading circuit, DRC. So I would like you also to try that if you want to see how that works and how to work with this. And of course, if you have time left, which I'm not sure you will, but you're welcome to try this at home or later on today before the end of the school, we have some examples for quantum convolutional neural networks that you can train and play with. All right, so I'm going to turn over to Tom, maybe to run through the second half of the QML basics very quickly, so you have at least maybe 45 minutes to try some of the other things. And I'm going to, I guess, log into Zoom, right? So just a second. So
Right.
Hey, everyone. Can you hear me fine? And can you share my see my screen?
Yep, we can.
Perfect. Okay, so yeah, yesterday we basically finished this first part about like gates and circuits, and we had a short look at the exercises. And today I would like first walk through the second part of this first notebook, because it basically shows the basics of working with PennyLane for optimization and for quantum machine learning. And afterwards, you can then go ahead and explore the new notebooks, the QDNN, and also the DRC, and there are even more notebooks on there. But I think especially like the QDNN and the DRC are the first ones to look at. And yeah, so let's get started. I think some people yesterday already got to this gradient part. And basically, this is like the core functionality about PennyLane that's so valuable, because everything we did before, you can also do it with, for example, QUC. But the quantum machine learning part, so basically the evaluation of gradients of quantum circuits, is the one that makes PennyLane so powerful. And so, yeah, basically we can define a Q node here, and this Q node can take parameters, right? This is what we want to have if we want a PQC, a parameterized quantum circuit, and you just give the function some parameters here, and you can then use them in your circuit. For example, for an RX gate, right? So you define like a parameter, which is then the angle for your rotation. And yeah, this way we can define a parameterized quantum circuit, basically. And you can then plot it again. Here you have to make sure that you give the plot function all the parameters it needs, because it will actually show it's only able to plot the circuit for given parameters and not for arbitrary ones. And so then, yeah, we can basically evaluate the gradient. And this is like the nice thing of PennyLane. You can just say, give me the gradient of my circuit, and specify which argument you want to compute the gradient for. So you could, in principle, also give it another argument for data. And we don't need gradients for input data, right? Which we want to embed, for example, in angle embedding or whatever. We don't need gradients for that. We only need gradients for the parameters, and so you can specify for which arguments of your circuit you want to get the gradients for. And this returns a function, and you can then evaluate the function and get the gradient, basically. And that's it. It's that easy. So some questions already came up yesterday. How is that gradient computed? And so if we use this one here, it basically, so PennyLane implements many different methods for computing a gradient. And if you don't specify anything, it will automatically detect which method is the best one in your case, given for your device. And usually, if we, for example, use the inbuilt Lightning qubit device we used before, it's usually a joint differentiation, because it's a very fast method. Since when we are simulating quantum circuits, we always have access to the state vector, right? That's not the case on a quantum computer. We have to measure something. We don't know what the state vector looks like on a quantum computer, but on the simulator we do all the time. We have it in memory, and that can basically be used to do and undo unit tests and compute gradients very fast in this way. But on a actual quantum computer, that does not work, and there you usually use the parameter shift rules that we learned about today in the lecture. And yeah, all of this is basically handled automatically in PennyLane, and you don't really have to worry about this. And yeah, moving on from that, or are there any questions maybe? If not, then yeah, you can also, of course, ask later on Slack. And yeah, moving on, if we can compute gradients, we can then basically optimize
Excuse me?
Yes.
Yeah. So for me, it's that. Can you speak a little bit slowly?
Yes, sure. Sorry. Okay. Yeah. So you can then, if you have a gradient, you can basically do gradient descent, right, and optimize like whole programs. And to do that, we have a little example in this notebook. So you can maybe run through it yourself later. Basically, what we want to do is, in this example, we want to compute the inverse of some unitary transformation. And usually you can do that analytically, but in this case, we want to choose some kind of ansatz with parameters and then optimize the parameters to give us our inverse of our unitary transformation. And this is then done by optimizing some kind of loss function, just like you do in classical machine learning, right? Where you have a loss function, an objective, and then you can do like back propagation by computing the gradients of your parameters of your neural network, or for example, in classical machine learning. In this case, we would have like some quantum circuit. And so, yeah, this is what we are basically doing. This is the ansatz we choose in this case, which is like some rotational gates and a CNOT for 2 qubits. And we basically want to compute a unitary, which is the inverse to the unitary which creates the base state, which we looked at yesterday already. And we know what it would look like, right? It's not hard to find, but in this case, we want to find it through like numerical approximation by optimization. And we know that if we apply U1, so basically the unitary which creates the base state, and then the unitary we want to find, we get the a 1. So basically we get the state 0, 0 at the end. This is what we want to get. And we want to find a unitary which creates the state. And to do so, we would create again a Q node, and there we have our first part of the circuit and our ansatz, and then we return some measurements. In this case, we measure both qubits, and we want to measure them in a way that we obtain the 0 state after applying U1 and U2 to our initial state, which is also the 0 state. And yeah, this is our circuit. If we plot it, this is like our U1, the unitary which creates the base state, and this is our ansatz, where the angles are then arbitrary. We want to find them, and these are 2 measurements. You could again measure this in a different way. For example, give like the complete computational basis for penny lane, but this is like sufficient because we know what state we want to have, and then we can build an easy loss function from it. And yeah, then here we do write our actual loss function. So it's just a function. It takes the parameters. In this case, I just call the circuit, right? This is the circuit I want to optimize. I just call the function, and what I will get is an array which returns the expectation values of my function in the policy basis. So this will have 2 elements because I'm doing 2 measurements. And the cost function, I build the loss function.
Excuse me. So I have a question. So here you have this RG gate and the CNOT and the RX gate.
Yes.
But can I also implement RY instead of RX? And what's the reason that you have this RG RX?
Yes.
The
So
RG.
exactly, that's a good question. So this is just an ansatz, and the choice of this ansatz is, I would say, not arbitrary, but you can choose in principle anything. It just has to be, we would say, expressive enough to express the circuit we want to find, right? So for example, do you think you could delete the CNOT gate and it would still work? Would the circuit still be able to be the inverse of this part here? Probably not, because we do not have a 2-qubit gate, right? And if we entangle 2 states with a 2-qubit gate, you would expect that you also need a 2-qubit gate to undo it. And yeah, you can try out different ansatzes for sure. I think that an ROI should work probably, but yeah, it depends for sure. But good question, yeah. And that's a big thing in quantum machine learning, right? You want to find an ansatz which is expressive enough to approximate your unitary, and then you can basically do studies about expressiveness of a certain ansatz and entanglement of a certain ansatz to choose. And you can play around a bit with it and see like what ansatz will work in this example, for example, and what does not work. Does that answer the question?
Yes, thank you. Yes.
Great. We can also follow up on Slack if you want to discuss more. So yeah, now I want to build the cost function from this. And so in my example, I want to obtain the 0 state after applying these two unitaries, U1 and U2, to the 0 state. And so I just want to measure and see if my state for the given parameters is in the 0 state. And to do that, I can build this cost function where I take the parameters, call the circuit, and if it's in the 0 state, the measurement in the Pauli Z basis will give the eigenvalue 1. So if both my states are in the 0 state, this optimized circuit will return an error which is 1, 1. If I sum over it, I get a 2 divided by 2, and then 1 minus the whole thing will give me 0. So I have a cost function which is 0 if in the end my state is in the state 0, 0. This is exactly what we want. Now we just have to minimize this cost function because, yeah, at its minimum, we will have, we will basically have the parameters we want. And to do so, we again like define parameters with the require squared true keyword. That's very important because this is not in the usual NumPy, right? And you need this for Penny Lane to understand, okay, I want like to calculate gradients inside of my quantum circuit. So this is very important. If you don't specify it, it will probably not work. I didn't try it, but it most likely will fail, I think. And then we can use like an optimizer, just like you know from classical machine learning. For example, Adam, which is like one of the standard optimizers, and they are also implemented in Penny Lane. And he basically takes care of everything. And now I can just take optimization steps through my cost function and optimize my parameters, update them, and we will see that our cost function will go to 0, just like we expect. And yeah, that's basically the optimization already done, right? It's only doing optimization steps in this case because we don't have a data set or anything, but we just have a loss function we want to find the minimum of. And then in the end, we can check the parameters, what they look like, and we can see that if I now call my optimized circuit with this parameter set, I will get the numbers 1, 1, which is exactly what I want, right? Which is
excuse me. So I have another question. I'm sorry to keep asking question.
so good.
Yeah, it was very surprising to see the cost as 0, ideally. So is there any magic that you have the cost function to be 0? Because this is because of the analytic calculation of the derivative and so on. So
yes. So you ask why it goes to 0?
Yes.
Yes, this is all built in basically in this optimizer, right? This is like a gradient-based optimizer, and what the optimizer will do in this optimization step is basically calculate the gradient with respect to the parameters of the cost function, then go a step into that direction, update the parameters.
Yeah, so usually in the machine learning, that through the experiences, maybe 90.999 or not 100% classification.
Yeah,
so here the 100%, right? So
I mean, you can see it over here, right? It's not exactly 0, 0, 0.
Yeah, but we don't have a data set, right? In classical machine learning, we would have a data set where you have to, maybe you want to fit something on the data set, but in this case, you have an exact solution, right? I know that I can set the parameters to a value where the outcome is 1, 1. So I know that there's a parameter set which sets my loss function to exactly 0, and we can reach it. Like, it's not perfect because of no X, but in principle we can do that. And in classical machine learning, if you, I don't know, want to classify MNIST, that's not the case, right? I mean, that's the case if you overfit terribly, probably, but I mean, usually that does not happen, but here we don't have a data set, so that's the difference.
Tom, so I think here we reached the part where maybe the rest is an exercise for the GHZ, right? So maybe we need to leave enough time for you to try it. So if you've already done this, you can go ahead to the neural networks. If you haven't done it, you can try to optimize the GHZ. And maybe we'll encourage everybody to ask their questions on Slack, like last time. And we'll let you maybe explore for the next, let's say, 10 minutes. This part, 10, 15 minutes. Depends where you are. If you've already done it, go ahead to the next. If you're not, you can try this part. Yeah. Right, Tom? Does that sound like a good plan?
Sounds good.
And we'll come around, I guess Jack and I will come around here and answer any questions if you have questions. But try to post them in Slack so that Tom can see them as well. Thank you. Yeah. In principles, we also have some solutions posted, and we'll post all of the solutions eventually too. But try not to look at them at first, right? Only if you're really, really stuck and need help, ask. Yeah. let's say maybe another 5 minutes on this task. If somebody doesn't completely finish, you can then, of course, follow it later. But then we can move to quantum neural networks. Yeah. All right, so maybe let's say a couple more minutes on this exercise, and we'll continue to the next part. Don't worry if you haven't finished, you can take your time a little bit later to do it. Or you can just run through and see how it works through the solution. probably didn't hear since I was muted. Yeah, I was just saying they should pick either the QDNN or the data reuploading next. And for QDNN, do you want to go over the circuit real quick? Yeah.
Yeah, sure. I can share my screen. Oh yeah, you're sharing. Great. Okay. So yeah, so basically this is like comes back to the question we had before. We have to choose some kind of ansatz in order to represent our PQC. And in this case, what we have here is an arbitrary 1 qubit rotation on every one of the qubits, and then a circular entanglement basically of all qubits. And this is like something that's quite often used because it shows that the circular entanglement gives you a good amount of entanglement, and that's what you want if you do quantum computing basically, right? Because you want to have like a good relation between all the qubits, and the circular, the single qubit unitaries give you a good amount of expressiveness basically. And yeah, but in the end, this is like quite heuristic, right? This is just what people use, and there are studies on really on what kind of ansatz to use, and this is quite famous. And one thing I just wanted to mention, because the question came up, I don't want to drag on for too long, but I think it's important. In principle, if you have an n qubit unitary, the dimension of that is, so it's a matrix basically in the group SU2 to the n, right? And the dimension of that is always 2 to the power of 2n minus 1. So for a single qubit, that's 3. And for 2 qubits, that's 15. And for 3 qubits, you already have 64 minus 1, so 63. And you see it goes exponentially. So for larger amounts of qubits, you have no way basically of representing this whole space with an ansatz, and so you have to make clever choices basically. And for a DNN, this is one of the choices people find to be very useful. Okay, yeah. And so yeah, with this you can then define a training circuit. And the thing that's new in this notebook is that we will loop over data actually, which we didn't do before. And so yeah, the circuit you saw right there was really just embedding, PQC, measurement. And yeah, for classification problems, it's nice to have like this hinge loss shown there, because when you measure in the Pauli Z basis, you get 1 and minus 1 as eigenvalues. So it's nice to have the same as labels for your data, because you can just write an easy loss function for it.
Very good. So thank you, Tom. Maybe we'll let you explore this notebook a little bit on your own, ask questions, post them in Slack or ask one of us. And whatever you don't finish today, you can take home with you.